Let's look at a few more cases as we've discussed earlier. Uh, yeah, what we have seen earlier, we have seen if x is a random variable, then if y is equal to g of x is a function of the random variable, this is also a function, this is also a random variable, provided it satisfies our g of x is a nice function. Okay, and we have seen few transformations. I mean, especially we have seen a transformation where y is equal to a into x plus b. This is known as a affine transformation. As a consequence of this, we've seen the distribution function of y is equal to the distribution function of x, and we substitute small x by y minus b by a. Right. Now, let's take another example where f of x is equal to the Gaussian density. Yeah. So normally the Gaussian density is uh, denoted, represented as n is equal to normal distribution of a mu and variance, mu sigma square. This is actually represented like this. But let's consider for simplicity n of 0, 1. So what does it mean? And this is sigma squared is equal to 1 and mu is equal to 0. So this will look something like 2 pi e raised to minus x squared by 2. It's a much simpler Gaussian, which is centered at the origin and which has variance is equal to 1. Okay, so what is fy of y if fx of x is a Gaussian? Fx of x, in the sense it is the density function, not the distribution function. So we know fy of y is fx of y minus b by a. So here we are not given the distribution function directly, we are just given the density function, right? So what is then fx? Fx is actually minus, so let me write it down here separately so that you have a better understanding. If f, sorry, we have fx of x is equal to 1 by root of 2 pi a raised to minus x square by 2, right? We know it is the integral from minus infinity to x f of x, that is 1 by root 2 pi integral minus infinity to x e raised to minus x square by 2, right? Okay, so if it is fx of y minus b by a, how will this integral vary? Instead of x, the limits will be from minus infinity to y minus b by a root 2 pi e raised to minus x square by 2 dx. So can we make it into a more relatable form, right? We already know that the integral of a Gaussian is another Gaussian. So you already know that. Keeping that in mind, you can do some change of variables to make it look like in the form we are used with or we are familiar with. It is a distribution function which we are familiar with. Okay, we can write this as, let's do some change of variables here. Let's make the substitution. D is equal to ax plus b, right? implies x is equal to t minus b divided by a. And what will, let me take it this to this side, right? Yeah. So then dt is a into dx, implies dx is equal to 1 by a dt. And substitute these values. When you substitute these values, what will it become? Yeah, minus infinity to y minus b by a. Y minus b by a. So yeah, one more thing we have to take care. Now, since we have changed the variables, the limits will also change, right? Yeah. So we know t is equal to ax plus b, which implies that x tends to minus infinity, t tends to minus infinity. The lower limit doesn't have much of a change. But when x tends to y minus b by a, t tends to a into y minus b by a plus b, right? What is it? A and a will cancel. This is y minus b plus b. Or so when x tends to y minus b by a, t tends to y. So our new integral will be integral minus infinity to y 1 by root of 2 pi e raised to, instead of x we have to write minus t minus b by a whole squared by 2 dt. But dt, it's not just dt, dx is 1 by a, right? There is a 1 by a here. Okay. So can we compare this to the standard form of a Gaussian? Whatever we have inside. Yeah. So what is the standard form of a Gaussian? Standard form of a Gaussian, n of sigma comma mu square is equal to 1 by sigma root of 2 pi e raised to minus, yeah, x minus 2a squared. There's no dt. So comparing this with this, we can get sigma is equal to a and b is equal to mu. So this is nothing but integral of a Gaussian distribution, right? So if this is the integral, what is its corresponding density function? Fy of y is normal distribution of normal, or the Gaussian distribution of b comma a square. B is the mean and a squared is the variance. Okay. So we have seen this. Another example. The next chapter we'll see how we can deal with uh, functions which are functions of discrete random variables. Right now we have dealt with functions of continuous random variables. Now we'll see how we'll deal with the functions of discrete random variables.